So, Lara, can you please
share? I'll share my screen. Hi. Okay. Can you see my slides?
Yes, and there are no Zoom boxes. Great.
You see the Zoom boxes also?
No.
Oh, no.
Oh, good. Oh, good.
Okay. That's fine.
Great. So now we have Lara Pantoni talking about unveiling the nature of 11 DSFGs. Please explain what that is.
Dusty star-forming galaxies. I
Very
will
good.
explain.
Please go ahead.
Thank you for the introduction. I'm currently a postdoc working at the Department of Astrophysics at CA in Paris with Frédéric Galliano, Susan Madden, and Anthony Jones on interstellar dust grain properties in nearby galaxies through spatially resolved spectral energy distribution fitting. However, today I would like to present a work I did during my PhD in CISA together with the group of galaxy formation and evolution. The main aim was to study the evolution of massive galaxy through a panchromatic approach applied on a sample of 11 dusty star-forming galaxies at the cosmic noon. And today I will stress the essential role of spatially resolved ALMA images to this aim. So first of all, dusty star-forming galaxies at high redshift have been discovered in the late 90s thanks to the first sub-millimeter surveys. And they were found to be an abundant population with that were very bright at sub-millimeter and far infrared wavelength. And later on, thanks to Herschel, we were able to discover more than 1 million of these high redshift galaxies. As you can see from this map, dusty galaxies at high redshift are the red points as they were imaged by Spire Herschel. Here I show a typical spectral energy distribution of dusty star-forming galaxies at increasing redshift. You can see that the emission is very attenuated in the optical band, while they are very luminous in the far infrared due to the dust thermal emission, and they can also reach far infrared luminosity higher than 10 to the 12 luminosity of the sun. They are very massive and they show star formation rates higher than hundreds of solar masses per year. Moreover, you can see that at sub-millimeter wavelength, they benefit of the negative K correction at the wavelength range that is actually sampled by ALMA. These galaxies were also found to account for the bulk of cosmic star formation rate density that I show here in this plot, and that actually peak between redshift 2 and 3. For this reason, to study these galaxies, it is very important for constraining massive galaxy evolution and the cosmic stellar mass assembly. Moreover, since the black hole accretion history computed through multi-wavelength studies is mimic very well the cosmic star formation history and peak at the cosmic noon, study these galaxies, it is also crucial to understand the role of galaxy black hole coevolution in driving massive galaxy evolution. But to this aim, we really need subarsecond resolution images of these galaxies. Before ALMA, indeed, the study of these objects were strongly limited by scarce spatial resolution. Indeed, if we want to observe at the cosmic noon, that means at redshift 2, we are actually in the most favoring, let's say, case to convert the angular resolution to linear resolution. So 1 arcsecond actually corresponds to 8 kiloparsec. But with ALMA, we were able to increase our ability to see this galaxy. You can see here, this is an image from the last survey. You can see that the Laboca beam observing at submillimeter wavelengths was of 20 arcsecond, while with ALMA we were able to identify the galaxy and to associate it with its multi-wavelength counterparts. So what we need is really to go at sub-kiloparsec scales to constrain processes that are happening inside galaxies, but also to very faint fluxes that is actually possible with ALMA, and it was not possible with the Scuba 2 or Laboca, for example. This is because the processes driving galaxy evolution involves baryonic physics that happens on galactic or subgalactic scales, meaning that we want to investigate scales that are smaller than 10 kiloparsec. This is very clear from this schematic view of a possible scenario for massive galaxy evolution, that is the in situ scenario, to which I will refer for interpreting the observational, my observational analysis. This scenario claimed that the main trigger of the star-forming burst and accretion onto central black hole is due to the early collapse of baryons into dark matter halo. Then, depending on galaxy mass, a certain fraction of the gas can cool and inflow towards the central region of the galaxy, where star formation ignites. And in the meanwhile, we have the central black hole to accrete material and eventually to become active and to produce outflows that can quench the star formation inside these galaxies. And then they will become the local massive early type galaxies. So this scenario, I want to stress that is also able to predict the V over sigma ratio that is measured in high redshift dusty galaxies, that is of the order of 10, as Fernanda was saying on Wednesday, and it was not, and hydrodynamical simulation are not able to reproduce. Moreover, I would like to stress that also interaction and mergings, of course, are important for the evolution, but they are not, and so they are taken into account, but they are not the main drivers of this galaxy evolution following the in situ scenario. So we had this sample that I selected in the submillimeter regime in the God-South field by requiring these galaxies to have a spectroscopical measurement of their redshift at the cosmic noon. Moreover, we require to have a very complete multi-wavelength sampling of this galaxy SED from X-ray to the radio band in order to constrain their emission. And to this aim, it was very important to have ALMA points, as also Tommaso Ronconi was saying yesterday, to constrain the far-infrared restraint emission from thermal dust. So we were able to model the spectral energy distribution of these galaxies in the very details, and this allowed us to characterize the integral properties of these galaxies. And by comparing to the prediction by the in situ scenario, we were able to let's say, interpret our results in the context of massive galaxy evolution. So what I want to stress is that these galaxies are very young, so the burst of star formation is between 0.2 and 1 giga-year, and they have a huge content of dust mass that was produced in less than hundreds of mega-year. And these galaxies have X-ray luminous counterparts, and two of them have X-ray emission dominated by the central AGN, while radioluminosity is always consistent with the star formation. That means that if an AGN is present, it should be radio silent or quiet. So what we expect in the end is that these galaxies will be quenched in some hundreds of mega-year by the AGN feedback and become local ellipticals. Then we wanted actually to look into the very details of the astrophysical processes happening at subgalactic scale. And for this reason, we look for submillimeter data by in the ALMA archive at the best spatial resolution available, and also we look for CO lines that allowed us to investigate the molecular gas phase of these galaxies. Here I show the ALMA contours overlaid on HST images. And you can see that 6 galaxies were resolved. Their radius, their radii were always of the order of 1 kiloparsec or less, and always smaller than the size, the optical size. This evidence could be interpreted in light of the size evolution predicted by the in situ scenario for these dusty star-forming galaxies. And indeed, we expect the UV optical light to partially emerge at larger radii. That is, indeed, you see that HST size that are the square that are in between the stability radius from to gas fragmentation and the rotational radius within which we observe the most intense dusty bars of star formation. We were able to confirm the scenario in which these galaxies are observed during the condensation of gas towards the center, where we have the most intense burst of star formation. Then, by the analysis of the CO lines that we detected for 4 galaxies of the sample, we were able to measure the molecular gas mass that was very high, larger than a few 10 to the 10 solar masses. And we also were able to measure or to give an upper limit on the radius of the molecular gas that was comprises between the ALMA radius and the HST radius, and of the order of 3 kiloparsec.
1 minute.
Thanks. By the analysis of the velocity and the velocity dispersion maps, we see that these galaxies are almost dominated by, the molecular component is dominated by a rotating disk of molecular gas. Indeed, you can see a very, very clearly the zero line here, and that is also peaked in the velocity, along which also the velocity dispersion map is peaked, while here probably we are looking at an age-on, a phased-on rotating disk of molecular gas, since the velocity map is consistent with zero and it is peaked in the center here. Peculiar case was the one of ALES 067. Indeed, you can see that there is no a very clear zero line here, and the velocity dispersion is peaked in the center, and there is this tail over here. So we look at the position velocity plot, and so what we conclude is, and we see that it is, we have some higher peaks quite far away at 500 kilometers per second. So what we conclude is that, of course, we should have probably a rotating disk of molecular gas that could be, but we can also could observe a possible outflow from the AGN at the very early stage. We also cannot exclude the scenario in which we are observing a galaxy interaction or merging, even if the maps are not enough disturbed actually, and the scale we are observing are quite small. Here,
please come to an end. You're ready.
Okay, so this is my summary, and what I really want to stress is that to disentangle the diverse scenario, we really need higher sensitivity and spatial resolution images, because what we have now is actually consistent to outflows, interaction, and so we really need this information for constraining better galaxy evolution at high redshift. Thank you.
Great, thank you very much. Also great to see that the ALMA archive was used for this.
Yeah.
I think we have time for one question.
Okay, so there are some in the chat. They will be posted on Slack. I pick one. So thanks for your excellent work. My question is, what is the redshift of 7 dust star-forming galaxies in UDF? If it is possible for them to associate with a protocluster, for me it seems to be a very overdense region.
The redshift is, what is the galaxy?
What is the redshift of the 7 dust star-forming galaxies in the UDF? So in the field.
Okay. So all the galaxies. Okay. So in the Hubble ultra deep field.
Yeah.
So these galaxies are all at more or less redshift 2, but they are not exactly at the same redshift. So here you see the redshift distribution, and it spans. So we have galaxies from 1.5 to 3 redshift. And so I don't think it is a protocluster actually, because so they are not so close, and I would have expected them to have exactly the same redshift, more or less, but it is not the case.
Okay, yeah, I think this answers the question. Yeah.
Great, thank you. I think there's another question, but we will put it in Slack, so maybe have a look there.
Okay, thank you.
Thank you very much. This concludes this session. So thank you all for all the speakers for these very interesting talks. Super nice to learn about all this different science.